Hi, in this video, we're going to take a look at how to apply some kinematic equations to solve various problems. These are going to be problems that happen on the horizontal. I'll post a lesson later on for how we deal with free fall, which is a special case of constant acceleration. In this scenario, we start off with a car. I know it looks kind of like a zucchini on wheels, but maybe it's the future. Yay. We have a car at rest, and maybe it's at a traffic light and the light turns green. And then it proceeds to accelerate at 2 meters per second squared. And in this situation, we're going to say it accelerates at 5.6 seconds, and we want to find out how far it goes and how fast. And then our car is going to continue at constant velocity because nobody should have constant acceleration forever, especially when there's law enforcement around. So we'll travel at constant velocity, and that'll happen for 25 meters. And then constant acceleration, the car needs to stop at the next traffic light. And if that's your experience in Burlington, it does often seems like one big traffic light. So you need to stop by 80 meters. And then the question for that is that how far is the car going to travel and how long is it going to take to stop and what acceleration is going to be necessary to come to a stop at 80 meters. Now, here's our reference point. We have to assign a place where we call 0. And then at various points along the way, we're going to keep track of how fast the car is going and where it is and time. And here's our 80 meters, and then roughly I've marked off intervals of about 10 meters just so we can get a sense about how things worked out. Because when you're solving physics problems and you get to an answer, it should sound about right. So for this part right here, we should get something that's maybe just a little bit more than 30 meters. Great. Well, let's go take a look at our kinematic equations. This can look a little intimidating, and but if you get used to it, it's actually not too bad, right? So here we go. These are the kinematic equations we left off with. Remember that this slide deck is on Canvas, so you can download it, you can print it, whatever you want to do. And we have a number of variables we're going to keep track of. So it looks like 5 variables to keep track of, but actually maybe 6 with this other x0 in case it has a head start. All right, so here we go. Let's start off with the constant acceleration. I find it useful to always list the variables. So let's just go ahead and list them all. So x0, x, v0, v, acceleration, and time. You know, it's nice to have a way of starting every time that's the same. So for our reference point, our car starts off at 0 meters. So that's 0. We don't know how far it goes in 5.6 seconds, so we'll put a question mark there, sort of a placeholder. Its initial speed, well, it starts off, the light has just turned green. So we're going 0 meters per second initially. We don't know how fast it's going to be going at the end, so that's another question mark for us. Then for acceleration, we know the acceleration is positive 2 meters per second squared. Often when we start doing this, people ask me about how many significant figures should we use, significant digits, and typically 2 or 3 are just fine. You're not going to lose any points, I don't think, for not having correct significant digits. Although you might get a frowny face, but we'll see. So 5.6 seconds. All right, well, let's start off with the how far. And if I go back and take a look at those kinematic equations, I want to make sure that I pick something that's going to answer the question about x. And I want to avoid any equation that has final velocity because I don't know what that is. So we go back and take a look at those kinematic equations. And yeah, the first one doesn't have final velocity in it, so that's a good choice. This one, delta x. Remember, delta x is x minus x0. Okay, great. So we're going to use equation number 1. So EQ1. So delta x, which is x minus x0 equals v0 t plus 1/2 a t squared. Okay, well, there's some things that are 0, so this is going to simplify. That means that our initial position is 0, and our initial velocity is also 0. And remember, it doesn't matter what the time is, 0 times any number is still going to be 0. So now I can put in some numbers, and remember, I'm looking for x. And that's 1/2. So these terms are all gone, 1/2 at squared. The a is 2. And then time is 5.6 seconds. And that's squared. Okay, so I'll do this on my calculator really quick. So 1/2, the same as 0.5 times 2 times 5.6 squared. And let's see where we land. And I get 31 point, I'm going to call it 31.4 meters. Okay, that's great. And we said it should have been a little bit more than 30, so we're right on track. So that's our how far. Now let's consider how fast are we going to be going. So let's do this in a different color. How fast are we going to be going? This is a question about velocity. And remember, we didn't know what the velocity is going to be. So I'll go back and I'll pick the right equation. So share screen. And this one looks like it's going to work. I know the initial velocity is 0 and the acceleration is 2, and I know the time, so this should give me the answer directly. So we'll use equation number 3. So for this question, we're going to go EQ3. And velocity equals initial velocity plus acceleration times time. Well, we're just going to plug in numbers. I know the initial velocity is 0 and the acceleration is 2. And the time is 5.6. I'm not putting the units in here because sometimes mixing abbreviations for units and variables is a little confusing. So I think we're there. So I just need to do 2 times 5.6 and sure, 11.2. Okay, so by the time we get here, we know that our velocity is equal to 11.2 meters per second. And we know the distance we traveled is 31.4. And we know the time is 5.6 seconds. Now we're going to continue for 25 meters. How long does that take? Interesting. So how long, even though it looks like it's asking for distance, is really a question about time. And so we want to find something that involves time and distance and velocity. Well, let's go ahead and write down those variables again. Right, so x0 equals x v0, final velocity, acceleration, and time. So when we hear a word like constant velocity, little alarm bells should go off in our head, reminding us this is a code word for acceleration is 0. I'm not going to write any units after that because does 0 have units? Deep question. Does it have a direction? All right. Initial position, that's 31.4. And that's going to continue for 25 meters. So my new position is going to be 31.4 plus 25. Right, so I'll just imaginarily write 25 underneath here. So the 0.4 doesn't get added anything. And 1 plus 5 is going to be 6. And 2 plus 3 is 5, of course. So that means if it continues for 25 meters, then its new spot is going to be 56.4 meters. The initial velocity is 11.2 meters per second. But since the acceleration is 0, I also know that the final velocity is going to be 11.2 meters per second. But I don't know how much time it's going to take, and that's actually what we're looking for. So it actually looks like equation number 1 is going to work, where I have x minus x0 equals v0t plus 1/2 at squared. Well, once again, there's quite a bit of cancellation. So this is like a cancellation fiesta then. Yeah. These two don't, whoa, wait a minute. So I'm going to do 56.4 minus 31.4. That's just going to be 25 again. That's easy. Initial velocity doesn't cancel. Oh, there's no cancellation at all. Okay, so let's see how this works out. So 56.4 minus 31.4, but actually I know that's just going to be 25, right? And initial velocity is 11.2 times the time, which we don't know. Oh, but look, it does cancel. The acceleration is equal to 0. Okay, well, when I subtract these two, I know this is going to be 25. And that's 11.2 times t. And so I divide 25 by 11.2. 25 divided by, I could just pull the answer I got from the last calculation. Yeah, 2.23. Now, that's not the total amount of time. It's just the time it took to go this distance from here to here. So 5.6 seconds to go from here to here. Then another 2.3 seconds. And then we have a bunch of questions here at the end. We have how far, we have how long, and what is the acceleration? So what are some things that we know? We know that the velocity is still 11.2 meters per second here. We know the position is 56.4 meters. I don't know the acceleration. I don't know time. So yeah, good luck, right? All right, well, let's go ahead and let's go back to share screen and find out what equation we can use here to help us solve this. And when I take a look at this, the key thing is I don't know time. That's really a big one. But the only equation that doesn't have time is this last one. So equation number 4. And actually, that's a pretty popular one to use. So equation 4. And that's going to be, whoops, v squared equals v0 squared plus 2a, calculator. Can you move over a little bit? Thanks, buddy. Times x minus x0. Okay, so I forgot. We should write down the things we know. So x0 and x, whoops, getting a little carried away here. v0, v, acceleration, and time. Let's write down what we know. We know the initial position is going to be 56.4. And final is 80. I usually do write the units here just so we can see if there are any unit mismatches. The initial velocity is 11.2. But then we want to be stopped at the 80 meters. So the final velocity is going to be 0. Notice how this is this variable right here. I'm just going to put a little asterisk next to it, Because this wasn't stated explicitly. This was implied that it comes to a stop. Right? You don't see zero written down anywhere here. So that frequently happens when we're solving problems, is that we have to identify explicitly stated variables and then the ones that are implied. But now I think we're ready to get going. So we know the final velocity is going to be equal to 0. That's cool. All right, so I can just do our little 0 right there. And so now 0 is going to be equal to, my initial velocity is 11.2, and that's squared, plus 2 times the acceleration. And now I'm going to subtract these two. I'm kind of running out of space here, but I think I can squeeze it in. Our final position is 80, and our initial position is 56.4. So 80 minus 56.4. Okay, great. Well, let's figure out what 11.2 squared is. Okay, and so I'm going to have 0 equals 125.4 plus, and now I can combine these two. So let me do 2 times 80 minus 56.4, 47.2. So 47.2 times A. Now to solve this, we want to get A all by itself. So we're going to subtract 125 from both sides and then divide both sides by 47.2. So that means 47.2 times the acceleration has to be equal to negative. Oh, negative, what does that mean? Right, well, let's finish the job. So I have negative 125.4 divided by the answer I got in the previous calculation, and I get a negative number. What? So that's negative 2.66 meters per second. Of course it's negative because it's slowing down. There are only 3 ways to accelerate: speeding up, slowing down, and then the third one is called changing direction. And we'll spend some time on that when the time is right. I've got how far, check, we did that. Took the difference between those two. And we've got how long. No, we don't. We have acceleration though. And now acceleration equals, and it sounds like probably equation 3 is going to be the one to do. So if I do equation 3, velocity equals v0 plus acceleration times time. We'll put in the numbers. We know the final velocity is 0. The initial velocity is 11.2 meters per second. And then the acceleration, I have to put that in as a negative number. So negative 2.66 times time. And so I move this over to the other side of the equation and divide both sides by 2.66. So my time is equal to and I don't want to put in a negative number here because when I move this over to the other side, it becomes positive. And so that's 2.66. Okay, so 4.2 seconds. And it comes out as a positive number, right? So if we hadn't have put this in as negative, then the time would have come out as a negative number, which we know time doesn't go backward. There's no such thing as negative time, right? Although, think about it. If you can put a negative number into your microwave, it would actually make things get colder. To think about that one for a while. Okay, next lesson is going to be about gravity.